Finite element analysis of axial bars. At the end of this section, you will be able to create the local and global stiffness and mass matrices for longitudinal vibration problems. You will be able to apply homogeneous boundary conditions to this model, and you'll be able to find the natural frequencies of these systems and show that these natural frequencies have converged. And finally, you'll be able to solve for the displacements in autonomous systems. So in this section, we are going to be applying finite element analysis method. What we saw previously is when we have these problems where we get a partial differential equation, we are able to find exact solutions to these continuous systems, but in a very limited set of circumstances. So we might have very limited geometries, the types of boundary conditions, the types of forcing functions where we can get a closed form solution. On top of that, we might not be able to deal with a change of density or Young's modulus or cross-sectional area because the PDEs that we came up with that we were able to solve by hand required these to be constant. And if one or many of them were not constant, we would have gotten a more complicated partial differential equation that might not have a closed form solution that we can obtain. Once we get to any problem that becomes a little bit more complex, a little bit more interesting, we might not be able to get a closed form solution, or it might be very difficult to achieve one. So a strategy when we have these more complicated systems is, instead of trying to solve a partial differential equation like we did for the simple case, we can actually change our methodology for solving these problems. So what we do with finite element analysis is we take our object, be it a beam in axial loading, as we're going to see in this section, or in transverse loading, as we'll see in following sections, and instead of treating it as one continuous object, we're going to partition it into small discrete pieces and then analyze them individually and see how they're linked together. So mathematically, what's going to be happening is, instead of taking our continuous system, which is a partial differential equation that might be very difficult to solve, by partitioning it into these small pieces, each of these small pieces is going to be its own ordinary differential equation, and we're going to have a set of them. So we're going from a continuous system, and we're going to be approximating it or changing it into a multi-degree of freedom system. And this then goes back to what we saw in Unit 2 with multi-degree of freedom systems, that when we have a set of ODEs, we do have strategies for solving them in the case where we have no damping, at least. We're doing this conversion and we're transforming our system from a continuous system to a multi-degree of freedom system. And this can be done in multiple dimensions. We're going to be doing it effectively in one dimension when we're talking about beams in transverse or axial loading, but it can be extended to 2D objects like shells and plates as well, and 3D objects, so whole objects that have volume. So what this is going to come down to is, when we have a complicated problem, we're often given this choice that either we can get an exact solution to an approximation of the problem, where we might have to really simplify the problem down or make a lot of assumptions about it in order to, for example, get a partial differential equation that works. So maybe we can say, well, basically the cross-sectional area is constant, so we can use this PDE to solve it. But we're now making an approximation to our exact problem so that we can get a closed form solution. Or, and this is what finite element analysis is doing, is we are taking the exact problem and we're going to be getting an approximation of the solution. So we are taking the problem, breaking it down into these small pieces, and solving it that way, and we get an approximation of the solution, and that approximation usually will get better and better and better as we take smaller and smaller pieces as we work through the mesh. So what is this mesh that we are going to be working with? Well, this is referring to how we are partitioning our beam or our bar or our object into these linked elements. So we're kind of taking our bar and turning it into a lot of little bars that are attached at what we call nodes. So each of these little bars we call an element, and where the elements interface with each other is what we call nodes. Now there's different ways we can be breaking up our system, different shapes we can break it up into. We're going to just be using rectangular elements for this course. And depending on the type of problem, might tell us what shape is best to break our problem into. Especially as we get into two-dimensional systems, maybe a rectangle is not the best, a triangle might be better, or some other shape. But it might be dependent on the type of problem we're looking at. Is it a modal analysis like we're doing here? Is it a static problem? Is it a dynamic problem? Is it going to be a thermal problem, an electrical problem? All those types of things are going to have some shapes and some methods that work a little bit better than others. But the basic premise we're going to be using here is when we mesh our object and turn it into these smaller shapes or these smaller elements, each of these individual elements, it will be true within an element that it has constant area, constant material, and depending on the type of problem, anything that would need to remain constant in order to solve an ODE at the elemental level. But as we go from element 1 to element 2 to element 3, each of those elements can have a different area and different material from any other element, but within each element we do make the approximation or the assumption that those things are constant. And we're going to see that this is going to allow us to analyze shapes or beams or bars that overall do not have a constant cross-section or a constant material, but break it up into a lot of elements where each individual one does have those properties being constant. And the elements that we break up our shape into do not have to be uniformly sized. We will be using uniformly sized elements in this course just because it's going to be simpler to do so, but there's no obligation to do so. In fact, we might not want to, on purpose, use equally sized elements. And this might happen if there's a part of the beam where we suspect something is going to be changing more rapidly about the stress or strain or whatever we're interested in. So if we have a beam, say, that has a hole in it, we might want a lot of elements near that hole. And as we get further from the hole where things are going to be pretty stationary or pretty constant, we could afford to use fewer and fewer elements as we get away from interesting features or rapidly changing features in our object. We are going to be compensating for the weight of our structure, both internal like a weight, but other forces that might be external, but always those are going to be placed on the nodes, never along the span of one of our elements. And what we're actually going to be solving for is the movement of our nodes. So in a continuous system, we were able to tell what was the deflection along every point in the beam at all points in time. What we are going to be losing here is we're only going to be able to analyze the movement of the nodes in the beam, not every particle in the beam. So the more elements we break our beam into, the more nodes we're going to have, and the finer and finer grain detail we're going to have of knowing how these nodes are moving. But it's still going to be this discrete process where we can only analyze the movement of nodes that we are creating. And what we're going to be focusing on is really what we call modal analysis. We're going to have some bar, some beam with a more complicated geometry than we would be able to analyze using the continuous approach, the partial differential equation approach. And we're going to still be interested, though, in finding out what are the natural frequencies and the mode shapes of these more complicated geometries. But we're going to have the issue to worry about that when we go from a continuous system to this multi-degree of freedom system, remembering back to Unit 2, we only can find as many natural frequencies as degrees of freedom of our problem. So if we make two what we call coarse a mesh, not using that many elements, not creating that many nodes, we're not going to be able to even find many of the natural frequencies. If we use a finer mesh using more elements, more nodes, then we're introducing more degrees of freedom into our system, and we're going to be able to then find more natural frequencies, more mode shapes of our system. As a general rule, the more elements and the more nodes we use in our mesh to to partition our system, the more accurate our values, the more accurate our estimates are going to become. Now, at a certain point, this becomes untrue. If we use too many elements and each one becomes too small, we actually are going to start introducing errors in our calculation just because we're going to be dividing by such a tiny number that it's going to lose some accuracy. We probably won't see that in any sort of the elements that we're going to analyze in this course, but it is something that potentially can happen. So as we add a finer and finer mesh, we get more and more of these natural frequencies. What's going to happen is actually the frequencies we gain are going to always be in order from the lowest to the highest. So if we only have 2 degrees of freedom that we split our shape into, we are going to be finding the first 2 natural frequencies. However, their precision and their accuracy are going to start off very poor. But as we add more degrees of freedom in our discretization, as we make this mesh finer and finer, we're still going to be finding in order then the first 3, the first 4, the first 5 natural frequencies, and so on. And what we're going to see is that the more elements we add, the better those predictions from lowest to highest of those natural frequencies are going to become. Now, what's the downside? Well, the more elements we use, the finer and finer mesh that we use typically is going to make the analysis slower. Both computationally and analytically, that's going to be the case. And as we add more elements, in general terms, the time it takes to compute the solution is going to scale with the square of the number of nodes, n, or the number of elements that we are using. So it's not going to be typically a linear increase, but this quadratic increase in time.